In this tutorial, we're going to look at assemblies. An assembly is just a file that imports other files. So if we've drawn some parts, then we might want to know whether they all fit together. We can verify this by drawing them in an assembly and then either just looking at the assembly or, for example, running a programmed interference check. So here, for example, we can see the parts for a 5-sided box. So the gray part here is the base. It sits flat on the table. Then the tab here at the bottom of the green side goes in the slot in the gray base. And the tab here on the green side goes in the slot in the magenta side. So they all hold together more or less without any glue. So I've already drawn these 3 different files, and what we're going to do is to start with an empty file and assemble them. So to do that, I'll choose File, New. In SolveSpace, there's no distinction between an assembly file and a part file. An assembly is just a part that imports other parts. So here, to import something, I'll hide the text window, and I'll choose New Group, Import Assemble. I'm given a list of files, and I'll choose Box Base. So if I zoom out, and if I rotate around, then we can see that our sketch now contains that base. If I grab a point on that base and I drag, then we can see that we now have a part that is free in space. So as imported, the part is not constrained in any particular way. We can put it anywhere. We can also drag its rotation. So if I grab this normal, which is drawn as an arrow, and I drag, then I can rotate it. The same's true if I grab a point and I shift drag it. So as imported, this part has 6 degrees of freedom. These are the same 6 degrees of freedom as any rigid body that's free in space. We could make our assembly simply by dragging around and trying to put all the parts roughly where they should be. But that would not be a very rigorous way to do it. So what we really want to do is constrain. I know, for example, that this normal on the imported part should be in the same orientation as the z-axis. So I'll choose Constrain, Same Orientation, and we see that the part has snapped to the desired position. But the translation of the part is actually still free. We've constrained the rotation of the part, but not the translation. So the part now has 3 degrees of freedom, 0 rotational degrees and 3 translational degrees. We can lock the translational degrees with a point coincident constraint. I'll say, for example, that this point and this point should lie on top of each other. So constrain on point. So now, if I try to drag any point on the part, nothing happens. We're fully constrained. This means that we're ready to import a second part. So I'll choose New Group, Import Assemble, and I'll choose the box side. So now we see that there is a second part in the sketch. It's in the wrong orientation, but we can fix that. We'll do that by shift dragging that point. So now I don't have it completely in the right orientation, but I have it kind of close. And that means that we can place a constraint. So I'll choose this normal on the imported part, and I'll choose this coordinate axis, and I'll say that they're in the same orientation. And it snaps to the desired rotation. Now, as I drag the part, we notice that I can drag the 2 parts so that they interfere. This is not actually an error right now. So if we look at the text window, then we see that the part is being imported as union. This means that the 2 parts are being merged in just the same way that 2 extrusions would be merged, for example. It's not a problem if they interfere. The solver just calculates the union of the two. We could also merge them as difference, in which case we see that the side is now cutting a slot into the gray base here. And if we move it, then we see that that slot moves around. But the option that we really want, most likely, is to merge them as assemble. So here, what I can do is I can choose merge as assemble. And if we look, then we see that any interference is drawn in red with black stripes. And we also see here in the text window that it reports the error with a little message. So merge as assemble verifies that the parts do not interfere. And if I drag them so they don't, then there's no more error reported. So to place the part, I'll just use a point coincident constraint again. I'll say that that part and that part have that point in common. And when I do that, we see that there is no red with black stripes, which means that there's no interference. So I'll repeat this process with a second copy of that identical part. Once again, it comes in interfering, which is not an error because by default it's merged as union. It would be if we merged as assembly. So I'll drag it somewhere reasonable, and I'll get it in kind of the right orientation. And then I'll say that this normal and this normal are in the same orientation. Notice that the two normals that I constrained here are actually pointing in opposite directions, but that's okay. The same orientation constraint does not enforce only a single orientation. It actually enforces one of 8 orientations. It means that the two normals have to be parallel, pointing in the same direction, or anti-parallel, pointing in opposite directions, and that the frame that rotates about that normal has to be aligned in an integer number of 90-degree steps. So this constraint would still hold, for example, if this side were exactly upside down, or if it were rotated 90 degrees to the right or left. That's why we had to drag the part into the approximate correct orientation before we applied the constraint. If we didn't do that, then we would have no guarantee that the solver would find the desired solution of those 8. To finish, I'll place the translational degrees of freedom with a point coincident constraint. So this is complete. We'll now add the magenta sides. So I'll choose new group, import assemble, box other side. And as usual, I'll drag the part roughly into the desired orientation. This normal and this normal are in the same orientation. And I'll say, for example, that this point and this point are on top of each other. So far, notice that I have always constrained the part with a single point coincident constraint and a single same orientation constraint. This is a good choice. The same orientation constraint restricts all of the rotational degrees of freedom, and the point coincident constraint restricts all of the translational degrees of freedom. So those two constraints will always lock the part in space. If it's possible to use that combination, then it's a good idea to use it because it's easy to understand. But that's not the only option. So I'll import our last side. Drag it into position, and I will use the same orientation constraint again. But this time, instead of a point coincident constraint, I'm going to use point-on-face constraints. So I know that when everything is assembled, this point, for example, is going to lie on this surface. So I'll choose to constrain on point curve plane. In this case, it's plane. And we see now that if I drag the part, then here, in this plane, it seems to have 2 degrees of freedom. But here, off to the side, if I grab the part and I drag it, then I can only move it up and down. I can't move it side to side, because the point-on plane constraint has restricted it. So I also know, for example, that this point is going to lie on this face. And now we're down to 1 degree of freedom. We can drag it only side to side. I can finish the constraining by saying that this point has to lie on this face. And now if I look around, it seems okay. And if I make it merge as assemble, we do not get an error. So notice here that I needed 3 point-on-face constraints to do the job of 1 point-coincident constraint. So a point-on-face constraint restricts 1 degree of freedom. A point-on-point constraint restricts 3 degrees of freedom. In any case, our assembly is complete. We have the usual clutter from the datum stuff, and I can hide that. And that's our assembly. We can save our assembly in the same way that we'd save any other file. If I go back now and I open one of the parts, I'll open the base, for example, then I can edit this part. For example, I'll add a circular hole in the middle of the base. So we can see what the base looks like now. It's the same as before, but just with this one circular cutout. This means that if I go back to the assembly, then the assembly now has a hole in it too. So the assemblies remain fully associative. Any change that is made to the parts propagates into the assembly. This means that when SolveSpace opens the assembly, it also has to open all the parts. This may be an issue if you're trying to copy, for example, an assembly to another computer. When you transfer over the assembly, you also have to transfer over all the part files. Otherwise, when SolveSpace attempts to open the assembly, it cannot find the parts to import, and it therefore does not know what the assembly looks like.